Electrochemistry, which is Unit 2 of Chemistry, 12th standard. Electrochemistry is a study of production of electricity from energy released from spontaneous chemical reactions and the use of electrical energy to bring about non-spontaneous chemical transformations. So the first electrochemistry is of two types. One is a production of energy, production of electricity. Electricity is produced from chemical reactions. Electricity is produced, this is one. The second one is carrying out non-spontaneous chemical reactions via electricity. Electricity is produced via chemical reactions or spontaneous chemical reactions. The second method, non-spontaneous chemical reactions conducted via electricity. These are the two subjects or two topics under electrochemistry. And there are two types of electrical cell. One is the galvanic cell. Two, it is the electrolytic cell. In galvanic cells, electricity is produced, whereas in electrolytic cells, electricity is consumed. In galvanic cells, we produce electricity from spontaneous chemical reactions. In electrolytic cells, we conduct non-spontaneous chemical reactions using electricity. These are the two types of electrochemical cells. And Daniell cell, which is under the galvanic cell, which is basically, this is the cell. This is the Daniell cell, where zinc is used as the anode and copper as the cathode with a solid connection, and this being the solution. Zinc electrode is used in zinc sulfate solution, whereas copper electrode is used in copper sulfate solution. And when external voltage applied in this cell is less than 1.1. 1.1 is the E potential of the whole cell. EMF of the cell is 1.1 volt. And when there is an external voltage applied to the cell and it is less than 1.1, it is what we have here. There is current flow. Electrons flow from zinc rod to copper, and current will flow from copper to zinc, and zinc dissolves at anode and copper deposits at cathode. When external voltage is equal to 1.1, there is no flow of electrons or current. No chemical reaction will happen. When external voltage is more than 1.1, more than the cell electricity, cell potential, then electrons flow from copper to zinc and current flows from zinc to copper. Zinc is deposited at the zinc electrode and copper dissolves at the copper electrode, which is reverse of what we see the mechanism in the Daniell cell. This happens when we apply an external voltage of more than 1.1 volt, and this energy from the galvanic cell is due to the change in the total Gibbs energy of the substance. This is a reaction of the Daniell cell. Daniell cell's overall reaction. And Daniell cell comes under galvanic cell. The reduction half reaction occurs, yes. And half cells, these half reactions where copper 2 plus is getting reduced by taking 2 electrons and forming copper, which is called the reduction half reaction. And here zinc getting oxidized by giving 2 electrons is oxidation half reaction. This both copper Cu2 plus and copper are referred to as redox couple or half cells. The same is true for zinc and zinc 2 plus as well. These both can also be called as half cells or redox couple. Standard electrode potential is nothing but the tendency of any metal ion to accept electrons and become neutrally charged. The tendency of metal ions to accept electrons and become neutral metal, and the tendency of this metal to undergo this reduction reaction is what we call standard electrode potential. And if we want to find the total EMF of a cell, this we find out by the difference between the E right side of the cell, the electrode potential of the right side, which is the cathode, the electrode potential of the cathode, minus E left, which is the anode. How to remember this is right red cat, meaning right side, reduction, and cathode. In reduction, right side in the Daniell cell, we see that the right side is copper. Copper undergoes reduction reaction. Copper ion will accept the copper ion Cu2 plus will accept electrons and be deposited on the copper, becoming Cu solid. This is the reduction reaction. As such, it is the right side. This is the standard convention representing cathode on the right side of the cell. Cathode, cat, reduction, right side, reduction, cathode, right red cat. and left side anode oxidation. Here we see that zinc on the electrode here is getting dissolved in the solution by becoming zinc 2 plus and giving electrons here. Electrons is given in the electrode. These electrons will move. This is what creates the current. And this is left side, represented conventionally left side in a cell, anode and aux, left and aux. These are the remembering methods. Yes, as I was telling before, the total potential of a cell, we can only find the total potential of a cell which is using a voltmeter or any kind of other detectors. We can only find electrode total potential of a cell. We cannot find individual electrode potentials. For example, E Cu2 plus to Cu, this kind we cannot find, which is here. We can only find the E total potential of the cell. So how to find these means we find this with respect to hydrogen. E cell, we take 1 as the normal cathode, as the right side is Cu2 plus to Cu minus E. We have a special standard hydrogen electrode which we take that it has 0 volt of electrode potential. Electrode potential will be 0 volt. We take that assuming the hydrogen electrode, the standard hydrogen electrode, will have a 0 volt potential difference. So we take one side, we take copper or whatever metal we want to find the electrode potential of, and we take standard hydrogen potential. As this will become 0, we will find that the electrode potential of cell in case of copper will be equal to the electrode potential of the individual copper 2 plus 2 copper. In case of copper, this will be equal to 0.34 volt, meaning that copper is more reducible in comparison to hydrogen. But in case of zinc, if we take zinc, is zinc 2 plus to zinc is negative 0.76, which is negative because H plus can more easily reduce to H2 than zinc getting reduced to zinc normal or zinc neutral. This has more tendency to happen than zinc getting reduced. As such, compared to hydrogen, the potential is negative. When we see that the standard electrode potential, the SRP value is negative, that doesn't mean that it is impossible for the specific metal to get reduced. It just means that with respect to hydrogen, it is more or less, like in case of negative, the metal's tendency to reduction is less than hydrogen. But in case of positive, it means that the reduction tendency of the metal is higher than hydrogen. This is the reaction. of the standard electrode potential. And the standard electrode potential is always taken when the oxidation, reduction concentrations are in unity, are equal. Standard is represented by this E naught. E naught meaning it is standard, meaning the oxidation and reduction couples concentration is in unity. When we take in realistic situation, most of the time this is not possible, when the unity is not mostly possible. As such, in realistic situations we used the Nernst equation, which will give us the normal potential. The Nernst equation, we have assumed the previous section the concentration of all the species involved in the reaction is unity. There is no need to always to Nernst showed that for the electrode reaction Mn plus is the standard reduction reaction where the metal ion is gaining electron. And what Nernst equation is, this is the where E Mn plus to Mn will give the not standard but electrode potential in that situation, or tendency of the metal in that situation to undergo reduction, where the E Mn plus to M equals the standard electrode potential of the cell minus RT, where R is the gas constant, T is the temperature in Kelvin, by N. N is the number of electron. If Mg2 plus to Mg, the electrons, Mg is gaining 2 electrons, so the value of N here will be 2, at least in this case. And F is Faraday's constant, which has a constant value, and this is ln natural logarithm of concentration of M, the metal, by concentration of the metal ions. Here we can find that why they took here the concentration of metal as 1 is because they have considered the solid M, which is nothing but the electrode. The solid M is nothing but the electrode. In zinc we have the zinc electrode, which is the anode, and copper we have the copper cathode, which is the electrode. So this we can take it as it is in unity, but the concentration of the ions we take specifically. This is the stable giving the standard electrode potential with fluorine to 2 fluoride ions, this being the highest electrode potential, meaning fluorine gas can easily take 2 electrons to undergo reduction to get fluoride ion. This is reduction reaction, and comparatively to hydrogen it is very, very high tendency. Fluorine has a very high tendency to become fluoride ions, and as fluorine is having high reduction tendency, we can call fluorine as a strong oxidizing agent. As fluorine has a high reduction tendency or a standard reduction potential, we can call fluorine gas as a strong oxidizing agent. And when we see the least value, we see that it is lithium, meaning that lithium plus gaining electrons, this is a reduction to lithium, has an electrode potential value of negative 3.5, which means it has a very low tendency to undergo this reaction. But in a reverse way, we see it has a really high tendency of lithium metal undergoing oxidation reaction to give lithium plus ion. This meaning it has a really high oxidation potential, where that means if it has really high oxidation energy or oxidation power, we can call it as a strong reducing agent, as it will give electrons very easily. When fluorine, we say that it has high reducing power, we call it as a strong oxidizing agent, whereas here lithium having a really high oxidation power, we call it as a strong reducing agent. This is the relation between the equilibrium constant and from the Nernst equation. I'll do it later again. And conductance of electrolytic solutions, etc. This is the conductance. Let's just directly go to the topic we left yesterday. Yes. Now what and all we studied till here, till this point, is about galvanic cells. Now we will start about electrolytic cells and electrolysis. Now, in an electrolytic cell, external source of voltage is used to bring about a chemical reaction. Nothing but we use electrical energy to bring a non-spontaneous chemical reaction, a slow chemical reaction. The electrochemical process are of great importance in the laboratory and the chemical industry. One of the simple electrolytic cell consists of two copper strips dipping in an aqueous solution of copper sulfate. If a DC voltage is applied to the two electrodes, then Cu ions discharge at the cathode, negatively charged, and the following reactions take place. Basically, if we take a solution of copper sulfate, CuSO4 or Cu2SO4, it is CuSO4, a copper solution, and take two electrodes of anode, which is positively charged, and cathode, which is negatively charged. We take an impure solution of copper sulfate and we connect it to a battery. Then what happens is, at the cathode, Cu2 plus ions in the solution of the CuSO4 copper sulfate solution will be attracted toward the cathode take the electrons and be deposited on this cathode. Why this is used? Because copper metal is deposited on the cathode. At the anode, copper is converted into Cu2 plus by the reaction Cu2 plus. Thus, copper is dissolved, oxidized at the anode, and deposit at the cathode. This is the basis of for an industrial process in which impure copper is converted into copper of high purity. Here you take two copper electrodes here in this solution of the, we dip it in the copper sulfate solution, pass DC current. In the anode, copper will undergo oxidation, copper 2 plus electrons. This copper, this one will dissolve in the solution, whereas in the cathode, copper will take the electrons, get reduced, and deposit again on the cathode. With this happening, the impurities in the copper electrodes will be purified and settled down, which is called anode mud, and the pure copper will be deposited on the cathode. This is a basic purification process in the industry. Impure copper is made an anode that dissolves on passing current. As I said before, this anode here, which is a positive charge, is nothing but impure copper electrode, while the right side is made of where it is not anything else, but the impure copper will dissolve into the solution and again get reduced and deposit on the cathode, which will be of high purity copper. And pure copper is deposited at the cathode. Many metals like sodium, magnesium, aluminum, etc. are produced on large scale by electrochemical reaction of their respective cations, where no suitable chemical reducing agents are available for this purpose. Many impure substances, like we found in nature, that these metals are very impure, like magnesium, sodium, aluminum. This and all, using the same process, using electricity, will be purified. As we can't find reducing agent for everything, this is one of the most industrially used method to purify the metals. Sodium and magnesium metals are produced by the electrolysis of their fused chlorides, meaning MgCl, MgCl2, NaCl2, NaCl, and MgCl2 are both purified, is produced by electrolysis of an aluminium for aluminium oxide, Al2O3, in presence of cryolite. Quantitative aspects of electrolysis. Michael Faraday was the first scientist who discovered the quantitative aspects of electrolysis. Now Faraday's laws also flow from what has been discussed earlier. Faraday's laws of electrolysis. After his extensive investigations on electrolysis of solutions and melts of electrolytes, Faraday published his result during 1833 and 34 in the form of well-known Faraday's two laws of electrolysis. First law: the amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte solution or melt. Basically what it means is, basically Michael Faraday came up with laws. Basically Michael Faraday investigated aspects of electrolysis, published his work between the time of 1833 to 34. He published basically two laws, the first law and the second law. The first law says that in a reaction, in the above reaction we saw the purification reaction where impure copper was getting dissolved from the anode and getting deposited on the cathode. The rate of this reaction is he's saying that the first law, this rate of this reaction rate is directly proportional to the current passing through the solution. Amount of chemical reaction which occurs at any electrode during electrolysis by a current is proportional to the quantity of electricity passed through the electrolyte. Is directly proportional to current or electricity passed through to the solution, through the solution. This is the first law. Let's read the second law. Second law, the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Atomic mass of metal divided by number of electrons required to reduce the cation. Let's read it again. Second law, the amount of different substances liberated by the same quantity of electricity passing through the electrolytic solution are proportional to their chemical equivalent weights. Basically atomic mass of metal divided by number of electrons required to reduce the metal. Let's read it a third time. The amount of different substances liberated by same quantity of electricity passing through electrolytic solution is proportional to their chemical equivalent weight. Amount of substances liberated during an electrochemical reaction is directly proportional to the equivalent weights of the substances, which is nothing but atomic mass of metal mass by number of electrons required to reduce the cation, which is nothing but if metal n plus Ne electrons gives metal with zero charge, then this is nothing but the number of electrons. This is the second law, that amount of metal or substances liberated is directly proportional to the equivalent weight. As if there is less number of electrons and there is more atomic mass of the metal, the liberation rate also increases. There were no constant current sources available during Faraday's times. The general practice was to put a conductor a standard electrolytic cell for determining the quantity of electricity passed from amount of metal, generally silver or copper, deposited or consumed. However, coulometers are now obsolete, and we now have a constant current sources available and quantity of electricity Q passed is given by Q equals IT, which is nothing but the equation Q by T equals current, which is nothing but the definition that current is nothing but the flow of charges per unit time. Q here will be IT. During Faraday's time, there were no constant current sources, and the general practice in place of a constant current source was to put a coulometer, a standard electrolytic cell for determining the quantity of electricity passed from the amount of metal, generally silver or copper. By determining standard electrolytic cell, if they take a solution and they will connect it to the, like for the how much the measurement of the current, they will pass current through this, and based on the rate of the reaction they will determine how much of the current is passing through, like how much reaction happens, that much of the current they will assume. Basically silver or copper were used, deposited or consumed, as I said, based on how much the reaction undergoes, which is nothing but deposited or consumed, where the anode is consumed or dissolved and cathode will gain deposited. But here instead reverse it will happen. However, coulometers are now obsolete, like we can easily find coulometers now, and we have constant current sources available for quantity electricity passed by. Now we now based off, due to our advanced technology, we can easily measure the current without the use of electrolytic cells. Q in coulombs when I is in ampere and T in second. Q is charge, I is current, it's in ampere, and T is second. The relation is this one, Q equals IT. Here the amount of electricity or charge required for oxidation or reduction depends on the stoichiometry of the electrode reaction. For example, in the reaction Ag plus electron gives Ag neutral. So the stoichiometry, the amount of charge we require to oxidize or reduce, for example, if there is a metal with N plus charge, we need N plus electrons to completely reduce it. This depends on the amount of how much the charge, this is the electrons. This electrons, how much electrons we need to add to the metal in order to completely reduce it. This electron will depend on the stoichiometry, meaning the coefficient. If there is 3 metal, there will be 3 times N. If it is 4 metal, 4 moles of metal, 4 times N, etc. It will depend on the stoichiometry of the metal taken, metal ions taken, more specifically, the number of the metal ions taken, the charge. If there is N electrons, we will use, if there is N plus charge, we will use N electrons. If there is 2 plus charge, we will use 2 electrons. And basically what they are saying is the number of electrons required is number of electrons. Basically electrons is nothing but negatively charged particles, and we can call it as charge. Amount of charge required depends on moles of ionic solution, ions, metal ions. 2, it will depend on moles of metal ions is the first one. It will depend on the charge of the cation, charge of metal ion. That's what basically what they're saying. In this reaction, we see that they took 1 Ag and the charge on Ag is 1 plus. So the electron required would be, if we take 1 mole of Ag, the electron required would be 1 mole of electron. Okay, let's continue reading. 1 mole of electron is required for reduction of 1 mole of silver ion Ag. We know that charge on 1 electron is equal to 1.6 into 10 power minus 19 coulomb. Therefore, charge of 1 mole of electron is equal to Avogadro's number times charge of electron, which we will get it as Faraday's constant. The 96,487 coulomb per mole, which is the value of the Faraday's constant. The value of Faraday's constant, we got it as the value of Faraday's constant because we multiplied the Avogadro's number, which is 6 into 10 power 23, times the single charge on electron, 10 power minus 19, which we got it as 96,487 coulomb per mole of electron. This is the charge per 1 mole of electron, and this will be the Faraday's constant. The quantity of electricity is called Faraday, as during the old times, why they are mentioning the Faraday's constant is because instead of taking the standard Q value or charge value, is because during those times there was no current sources, there is no constant current sources available during Faraday's time, and the standard practice was using electrolytic cell and determining based on the rate of the reaction or the position of the reaction. Due to there being no amount or no indication of how much charge was used, Faraday defined a constant called Faraday constant, and this constant having a value of 96,487 coulomb per mole and represented by the symbol F. For approximate calculation, if we can use 96,500 as the approximate value. For electrode reactions, here in this both reaction we can find the amount of charge using in terms of Faraday. 1 mole of Mg2 plus is taken, and how much Faraday of electron we need is basically, because here 2 moles of electron is nothing but 2F. This is the amount of charge required to completely reduce 1 mole of Mg2 plus ions. In case of aluminium ion, we need 3F charge to completely reduce the aluminium ion into the aluminium neutral. It is obvious that 1 mole of Mg2 plus and Al3 plus require 2 mole of electron, 2F, and 3 mole of electron respectively, 3F. The charge passed through the electrolytic cell during electrolysis is equal to the product of current in amperes and time in seconds. In commercial production of metals, current as high as 50,000 amperes are used, that amounts to about 0.15 Faraday per second. Basically, they are saying that the commercial, like how much charge they use commercially, is approximately 0.518 Faraday per second. This value they calculated by using I equals 50,000 by the charge, the Faraday's constant, which is approximately 98,000, which we get a value of approximately 0.5 Faraday per second. This is the commercial unit. A solution of copper sulfate is electrolyzed for 10 minutes with a current of 1.5 amperes. What is the mass of copper deposited at the cathode? The time we should convert it into the SI unit, 10 times 60 being 600 second. Charge equals current into time, which is the basic definition, which is nothing but Q equals IT. Just erase this. Yes. Now I equals Q by T and Q equals IT. Charge equals current into time, which is the current they gave as 1.5 into times 600, which value we get it as 900 coulomb is the charge. According to reaction, as we see that it is getting deposited, which means Cu2 plus ions in this copper sulfate solution are getting reduced to form copper solid, which will get deposited the neutral zero charge. This is what they have written here. We require 2F because here copper 1 mole of copper requires 2 moles of electron, which is 2F to complete the 2F of charge to completely reduce this ion, this 1 mole of ion, to solid or neutral. So they used 2F, which is 2 into 96,000, to deposit 1 mole or 63 grams of copper. That is basically what they are saying is, if you want to deposit 1 mole of copper, we need 2 into Faraday, which means approximately 200,000 coulombs of charge if we need to deposit 1 mole of Cu2 plus on the electrode. So basically the equation will be something like this: 2F by 1 equals 900 by X, which is the amount of copper deposited. If X we take that side, it will be 900 by approximately 200,000, which we can write it as 200 into 10 power 3. Is this correct? Yes. 200,000, yes. 200 into 10 power 3, 0 cancel. 4.5, which we will get an approximate value of 4.5 into 10 power minus 3. Is it again? So it should get a value of approximately 4.5 into 10 power minus 3 moles, and this, if we divide by the molecular mass of copper, which is 63, we get an approximate value of 4.5 wait a second. This is still here we are correct. We got a 900 coulomb value and we need 2F or 2 into approximately 200,000 coulomb of charge to deposit 1 mole or 63 grams of copper, and for 900 grams the mass of copper deposited is, so 63 gram per mole times 900 by 900. So they took X by 900 equals 63 gram per 2F. This they substituted. This is their for 63 grams or 1 mole we need 2F or 200,000 coulomb of charge to deposit 63 grams. And so if we take 900 coulomb of charge, what will be the X value? It will be X equals 63 by 200 into 10 power 3 times 900. 63 times 9, you can write 4.5. 63 times 4.5 times 10 power minus 3, we will get an approximate value of 0.29 grams. This is the amount of copper from a copper sulfate solution which is deposited on the cathode when we supply a current of 1.5 amperes for a time of 600 seconds, and the charge we calculate is 900 coulomb. Now let's continue reading. Products of electrolysis. Products of electrolysis depend on the nature of material being electrolyzed and the type of electrolytes being used. If the electrode is inert, meaning kind of in standard electrode, standard hydrogen electrode, SHE, standard hydrogen electrode, we took platinized electrode as a surface, or a standard electrode as an inert electrode. Exactly what they are saying here. Example, we can take either platinum or gold. This electrode does not participate in the chemical reaction. That means this platinum will neither get dissolved in the solution nor will it be deposited on the electrode. As such, we call it inert. It does not participate in the chemical reaction and acts only as a source of sink for electrons. Because this as it is an electrode, charges will be flowing and it will give the electrons or take the electrons. On the other hand, if the electrode is reactive, it participates in the electrode reaction, as we saw in inert, meaning platinum or gold. But for a reactive electrode, we can take as copper electrode. We see that copper, in terms of Daniell cell, the copper electrode is getting deposited on, whereas the zinc electrode is participating on the reaction by dissolving in the solution. This zinc reduced keeps on decreasing as it is going to dissolve in the solution to give zinc 2 plus and give the electrons to the electrode. Here the electrode, in terms of Daniell cell, copper and zinc are both participating in the reaction, so we can call them as reactive electrodes. Let's continue reading. Thus, the products of electrolysis may be different for reactive and inert electrodes. The products of electrolysis depend on the different oxidizing and reducing species present in electrolytic cell and their standard electrode potential. The product electrolysis depend on different oxidizing and reducing species present in their electrolytic cell and their standard electrode potential. The standard electrode potential, according to IUPAC, is nothing but the reducing tendency of metal ions is nothing but SRP value, and this SRP value based on hydrogen. Let's continue. Moreover, some of the electrochemical processes, although feasible, are so low kinetically that at lower voltages this did not seem to take place, and extra potential called over potential has to be applied, which makes such a process more difficult to occur. Let's read the sentence again. Some of the electrochemical reactions, although feasible, are so slow kinetically that at lower voltages these do not seem to take place, and extra potential called over potential has to be applied, which makes such processes difficult to occur. Not all reactions, even though like it might be possible, it will take so long, so much time that it may seem that it's not even occurring. Like if we take two electrodes and for some metal it is getting deposited here, it's a reaction. We're not applying any electrode potential, but without any electrode potential it needs to deposit on this metal. What if it takes 100 years? It's not real, it's just an example value, for just one speck of the metal to deposit on this electrode. It takes a really long time, right? Even though it is happening, it is feasible, but it takes such a long time, which is slow kinetically. Now let's continue. And in order to make that reaction happen, we need to apply over potential. We need to apply over potential. We need to increase the potential. We should add extra. We should connect the battery to increase the rate of the reaction in such kind of cases. For example, if we use molten NaCl, the products of electrolysis are sodium metal and Cl2 gas. Here we have only one cation, Na+, which is reduced at cathode, Na+, plus E-, and one anion, chloride, which is oxidized at anode, becoming chlorine gas during the electrolysis of aqueous sodium chloride solution. The products are NaOH, sodium hydroxide, chlorine, and hydrogen. The alkali formation process. In this case, besides Na plus and Cl minus ions, we also have H plus and OH minus ions. Ions along with the solvent molecules H2O. At cathode, there is competition between the following reduction reactions. At cathode, this is only at cathode. cathode, you see that Na plus plus E minus. Sodium is getting oxidized to form sodium metal. The electrode potential is extremely less because sodium, as we know, is a really electropositive element and a very reactive element. Sodium, if we put in a water, it will explode. That much reactive agent which can easily give electron, if you want it to undergo reduction reaction, the potential is negative 2.17, which is really low. Hydrogen, as we know, the standard we take it as 0. The reaction with higher value of E is preferred, and therefore only this reaction will occur. Reaction at the cathode during electrolysis is hydrogen ion, H plus ion gaining electron. If there is 2 H plus ions, they will take 2 electrons. They will be liberated as hydrogen gas. But H plus aqueous is produced by the dissociation of H2O. H2O gives H plus and OH minus. Therefore, the net reaction at cathode may be written as sum of this and this. H2O plus electron gives hydrogen gas along with hydroxide ion. At anode, the following oxidation reactions are possible. Chloride ion gives chlorine gas and electron, where this chlorine is getting oxidized. This has a good potential, good standard reaction potential. And H2O, we have H2O becoming O2 plus 4H plus and giving 4 electrons. The reaction at anode with lower value of E is preferred, and therefore water should get oxidized in preference to chloride ion. However, remember, this is what is happening at anode. At anode, we see that oxidation is taking place at anode. Oxidation meaning it is losing electrons. What they gave here, it is reduction potential. So if the reduction potential is really high, oxidation will be really low. This tendency for chloride ion to undergo oxidation is less compared to water undergoing oxidation. If reduction potential is high, that means oxidation potential is low. Because chlorine has high reduction potential, its oxidation potential is low. Compared to water, which is 1.23, the chlorine has higher reduction potential. As such, water will have higher oxidation potential compared to chlorine. As such, where anode, where lower values of standard electrode potential are preferred, because of that, chloride instead of chloride ion, this reaction is more preferred. An account of overall potential of oxygen reaction 2.36. However, and normally that is the case. However, on account of over potential of oxygen reaction, the chlorine reaction is preferred. Thus, the net reaction may be summarized as NaCl reacting with oxygen. The dissociation of sodium chloride in water to give Na plus and Cl minus ions. At cathode, H2O getting reduced to give hydrogen gas and hydroxide ion. At anode, chloride ion getting oxidized to give chlorine plus electron, and net reaction being sodium chloride plus H2O gives sodium plus hydroxide plus H plus. The standard electrode potentials are replaced by electrode potential given by Nernst equation. Take in account the concentration effects. During electrolysis of sulfuric acid, the following processes are possible at anode. H2O gives O2 plus 4H plus electron. The reduction potential is high, but here it is getting oxidized. So the tendency for this reaction is less. Here, two sulfate ions are also getting reduced, are getting oxidized. The reduction potential is really high. So this reaction tendency, where this is going on undergoing oxidation, is also low. For dilute sulfuric acid, this reaction is preferred. But at higher concentrations of H2SO4, 2.36 is preferred. This reaction happens when the H2SO4 concentration is very less. Both this one as well as this reaction, both are oxidation reactions. Oxidation happens at anode, and at anode in lower concentration of H2SO4, this reaction is preferred, whereas at high concentration of H2SO4 at the anode, this reaction is preferred. Now let's see the in-text questions. If a current of 0.5 ampere flows through a metallic wire for 2 hours, then how many electrons would flow through the wire? What they give in the question is I equals 0.5 ampere. Time they gave is 2 into 2 hours, so convert it into minutes times 60 for seconds, which will basically be 120 times 60, 12 times 6, 120 times 60, which is 7200. Yes, 7200 seconds. This is the time. They're asking how many electrons would flow through the wire. If you want to find charge, Q equals IT. Q equals 0.5 times 7200, which is basically 0.5 times 7200, which is basically 7200 by 2, which is 3600 coulomb. This is the total charge, and if you want to find the total number of electrons, divide this coulomb charge by the charge of a single electron. 1.6 into 10 power minus 19, it will be 3600 times 10 power 19 by 1.6, which will be ones are approximately 2.3 something. 2.3 actually 0.1, so 2300 times 10 power 19, which we can write as 2.3 times 10 power 22. This many electrons will flow through the wire. 2.3 times 10 power 22 electrons. Now I'll erase this. Next question. Suggest a list of metals that are extracted electrolytically. We can take example of copper, sodium, industrially, magnesium, aluminium, etc. Where copper is extracted from impure copper from copper sulfate, sodium from sodium chloride, sodium and magnesium from fused chlorides, aluminium from aluminium oxide Al2O3. Third question. Consider the reaction potassium dichromate plus 14H plus electrons gives 2Cr3 plus 7H2O. What is the quantity of electricity in coulombs needed to reduce 1 mole of Cr2O7 twice? Cr2O7 2 minus. So basically, potassium dichromate is a really strong oxidizing agent as it can easily take electrons, and Cr2O7, the oxidation state of Cr2O7 2 minus, where the oxidation state of Cr is 2x equals 2x minus 14 equals minus 2, and 2x equals 12, x equals plus 6. Cr2O7 2 minus going from plus 6 to 2Cr3 plus requires 6 electrons, I believe. Yes, since a single chromium 3 plus ion needs 3 electrons, 2Cr3 plus ion needs 6 electrons. If we calculate this, 1 mole of dichromate needs 6 moles of electron, and 6 mole of electron is nothing but 6 times Faraday's constant, 6F. What is the quantity of electricity in coulombs? Or if you want coulombs, we can substitute 6 into 96,000, which is approximately 600,000 or 580,000 or so coulombs. Now next. Now the next topic being batteries. Any battery, actually a battery is nothing but a cell is what produces an electricity. A cell is represented like so. This is a positive, this is a negative terminal. A battery is a combination of one or more cells. 2 or more cells is what we call a battery. If there are 2 or more cells, we call it a battery. A single unit of a battery is what we call a cell. Battery may have one or more than one cell connected in series. Or cell that we use as source of electrical energy is basically a galvanic cell where the chemical energy of redox reaction is converted into electrical energy. However, for a battery to be a practical use, It is reasonably light, compact, and its voltage should not vary appreciably during its usage. There are two types of batteries. In the primary batteries, the first type is the primary batteries. The reactions only occur once, and after use of over a time, battery becomes dead and cannot be reused again. This is the primary. There are actually two types of batteries. Normally, battery is a connection of battery is a connection of many cells in series. But how this cell works is, what it does, it produces electricity or gives us electricity. We saw that the same thing happens in galvanic cells. Galvanic cells, using spontaneous chemical reactions, generate electricity. This is exactly the mechanism used in batteries as well. Batteries contain chemicals which undergo spontaneous reaction to produce electricity. And batteries are divided into two types of primary, which is one-time use battery, and secondary, and the second type, rechargeable batteries. Rechargeable batteries are batteries we see in mobile phones, laptops, etc. or many of the devices we even see in toothbrush these days. How this rechargeable batteries works is, normally how does primary batteries works is, the chemicals will undergo spontaneous reaction to generate electricity. What is the criteria for rechargeable batteries? For primary batteries, it is for the chemicals to non-stop undergo spontaneous reaction and produce electricity until the chemicals are used up. What is the second type of battery? It is a rechargeable battery. What can be the criteria for rechargeable battery? Rechargeable batteries should be something after one time use, it should be again recharged to be again used again. So how can we make batteries rechargeable? First, how do batteries produce electricity? The chemicals in them, from chemicals, if the cell contains chemicals of A and going from A to B, it produces electrical energy. Electrical energy is liberated or produced. This is the primary kind of reaction. And this is the primary usage. For the criteria of rechargeable batteries, the A should be converted to B. First time, the A chemical should be produced to B and electricity should be given. And for it to be rechargeable, this B chemical should again be reversible reaction to A chemical and it should take electricity. This is how rechargeable cells are supposed to be. The first A chemical will take the electricity. The first A chemical will undergo the reaction and give out electricity, whereas after completely giving out electricity, all the chemical in the cell will be converted to B, right? This B chemical, if we again charge a cell, which is by giving it electricity, should again undergo a reverse reaction to A chemical. If this undergoes, then the second time usage, again after charging, this A chemical will again get converted to B chemical. This will again produce electricity. This is how rechargeable cells should work. For an ideal rechargeable cell, this cycle of giving electricity and getting recharged should be many times. Even though if you use it many times, it should be usable again and again. This is for ideal rechargeable cell. Primary type of cell where there is no recharge is when a chemical will be there, it will convert to B chemical, electricity is produced, and we throw this cell. There is no use for this cell. There is no reversible reaction here. The chemical will already be converted and it will be over. So let's continue reading. In the primary batteries, the reaction occurs only once, and after use over a period of time, battery becomes dead and cannot be reused again. The most familiar example of this type of dry cell is known as Lagrange cell after its discovery, which is the most common type of dry cell is Lagrange cell. Lagrange is the one who discovered this cell, so it is named after him, which is used commonly. This kind of dry cell is used commonly in the transistors, clocks. The cell consists of a zinc container as an anode meaning oxidation. Zinc from the electrode will dissolve in the solution and give out electrons to the electrode, and the cathode is a carbon graphite rod surrounded by powdered manganese dioxide and carbon. The space between the electrons is filled by a moist paste of ammonium chloride and zinc chloride. The electrode reactions are complex, but they can be written approximately as follows. Anode zinc, as I said, this is the basic oxidation reaction of zinc, and cathode, this is basically the basic simple diagram of the cell is this one. This is a simple representation of the cell. So if we take a cell, the cell will contain zinc anode and zinc container. Zinc will give electrons, and a cathode will be there, which is of carbon, powdered manganese oxide, and something else of the cell consists of a zinc container that also acts as an anode, and the cathode is a carbon graphite rod surrounded by powdered manganese and carbon. The space between the electrode is filled by ammonium chloride and zinc chloride. The electrode reactions are complex. Yes. The anode is represented on the left side and it is of zinc. The cathode is graphite or carbon graphite. Basically it's graphite because graphite conducts electricity. Graphite surrounded by powdered MnO2, magnesium oxide. These are the two electrodes where zinc is positive anode is positive and cathode, which is graphite and surrounded by powdered magnesium oxide, is the cathode. In between is plates of with paste of ammonium chloride and zinc chloride. This is the basic representation of the battery. where zinc is the anode, graphite is the cathode surrounded by magnesium oxide, and the distance is filled by ammonium chloride and zinc chloride. పెడతాం.
కలిపించాను.